Welcome to qnawire.
In this problem, we're given that a spaceship of small mass, small m, is looping around and being slingshotted by the planet Jupiter. It enters with some velocity v1 and leaves with a velocity v2. And we're given that the mass capital M of the planet Jupiter is much greater than the mass small m of the spaceship. Now, whenever we have a situation in which there is a phenomenon that can be modeled by a collision, so you can look at this as the object coming in at speed v1 and leaving at speed v2, so colliding with the object Jupiter, and the mass of Jupiter is much greater than the mass of the spaceship. So we can model the situation using a barrier, because a barrier technically has infinite mass and its speed will not change after a collision. Now, speeds relative to the sun are given. So the spaceship is moving at a speed of 10.5 kilometers per second, and our barrier is moving at 13 kilometers per second. Now, we know that this collision is elastic. And how do we know that? Well, the energy must be conserved. So the initial energy must be equal to the final energy. And whenever that happens, the collision is elastic, and the speed of approach is equal to the speed of departure. Now, we also know that the barrier's final velocity is also 13 kilometers per second. So we're going to let v1 be the initial velocity of our spaceship, and that subtracted from v2, the initial velocity of our barrier, is actually equal to v3, that is the final velocity of our barrier, minus v4. That is the final velocity of our spaceship, and that gives, so v1 is 10.5 minus 13 is equal to v3 that we discussed is the speed of the barrier after the collision. Now, since the barrier has a much larger mass, its speed is not affected by the collision, so that remains 13 minus v sub 4. Now, this gives v sub 4 as being equal to so it's 13 plus 13 minus 10.5, and that gives us 15.5 kilometers per second as the velocity of the spaceship after collision. And that is our required answer.